So it's a pleasure for me to introduce Johannes Hölzl, who will talk about classical analysis, and Isabelle.
Yeah. So unfortunately, I will mostly talk about Isabelle's analysis because there is no analysis yet in me.
No, it's the end of part one.
But at least I have a couple of nice slides how we want to analyze at least the real numbers, and so that's more private. Yeah, so this is a talk together with Fabian, who provided us some slides. So first, a small outline. I will talk a little bit about the history of the classic or the analysis in Isabelle. Then also give an overview of the very foundation of how the type class structure works, but also some applications. Some important applications, especially ordinary differential equations from Fabian, and how we use them in measure theory, integration theory, and a little bit about probability theory. Then I want to also tell a little bit about decisions we needed to make to fit analysis into whole, especially in Isabelle's version of whole, problems you run into, and some of the solutions we have. And as I said, then I want to present yet another formalizations of reals. Yeah, first history. Fleury and Paulson, I think you started around the 2000s, mechanizing non-standard analysis, which gave us already limits. We could talk about derivatives, transcendental functions on reals, on complex numbers, and this RC star R and star C for non-standard analysis. But then Brian Hoffman introduced in 2006 type classes. I think a little bit before this was the type class concept introduced in Isabelle, and he used them to formalize vector spaces and talk about vector spaces and generalize the theorems we had here from on the concrete types of real numbers and complex numbers to real vector spaces. Then around 2008, Kalb and Robert Himmelmann started porting the Euclidean space theory from Holite to Isabelle. And this is a very interesting conversation where you essentially use a trick to encode Euclidean space by saying you have a finite type going a function space from a finite type into the reals to represent Euclidean spaces. And then it was variously extended, and very important what I want to explain also how these two steps actually merge together to say we port a lot of theory from Holite, but also we generalize to a more abstract setting and try to find a more abstract representation of most of the theorems. Since then, well, more theorems get ported, especially from Larry. You see a nice diagram. We use this to introduce measure and probability theory. As I said, we have ODEs. Manuel did a lot about asymptotic analysis, and Vendali did introduce algebraic numbers and then Cauchy residual theorem. And there's quite a large set now in of theories in the AFP actually using the analysis library. This is a small historic development. So I started here in 2010 because it was the first time when we had actually a directory where we could just count the lines of number in analysis. And around the same time, probability theory started. You may wonder what this jump here was. Actually, unfortunately, it was not that a lot of new theory was developed, but that Macarius decided to adopt the white space regime on the files. So the problem is, when Robert Himmelmann started to port Holite theories, he wanted to have it as short as in Holite, and wrote a couple of tactics in one line, which Macarius didn't accept. So this was one change. And you may wonder what happened here. Actually, we moved measure theory from probability theory into analysis. That's the biggest jump. But what you see here, I think you started to port more from Holite to Isabelle. And then, yeah, so I think at this point we have half of Holite's theory maybe now in Isabelle, so there's still a lot of stuff missing. You may also wonder why nothing happened here. So that's more like a problem with the diagram. I had hoped to find a way to nicely extract the amount of changes actually, how much lines changed, because what happened mostly here was that we tried to generalize this theory, going from Euclidean space into topological space, metric spaces, various kinds of vector spaces, and so on. Okay. So what do we have? We have this is just a lot of concepts. We have Stern-Weierstrass, we have characteristic extension theorem, we have different integrals, we have Gauss fixed point, Lebesgue integral, and so on. So I think we have a very nice collection of a lot of stuff which one wants to have when one starts reading a analysis textbook nowadays. What you also see is that half of the stuff is actually ported from Hölzl, and then just a couple of things actually developed new. But the interesting thing is that I think a lot of stuff we actually ported is expressed now in a more general setting. So first, I want to give a little bit overview of the type class hierarchy, as I said, and then I go into more concrete details and some concrete applications. Yeah.
Can we see?
This one?
Yeah. So for instance, Fubini-tonally is something about integrals.
Yeah, it says that
And you have several definitions.
yeah,
Does it mean you have
Fubini-tonally
this for all
is
the-
on, no, sorry. I mean, Fubini-tonally is on the Lebesgue-Wagner integral. So it's a measure theoretic concept. So I don't know if you have Fubini-tonally, for example, on the Heinz-de-Kurzweil integral. It's missing here.
More generally, my question would be, how does the different version of integral
Yeah,
interact?
I go to this. I have a couple of slides on this. Yeah, but this is a big problem, yeah.
I think there's a thing that John Harrison called the baby Fubini theorem, which is for the Hansstock integral.
Ah, okay, yeah.
I forget what Fubini's theorem says.
So Fubini says you integrate first over x and then over y, and then you can y and x. But it only works for, I mean, for measure theory it only works for sigma finite measures, but it should always hold for the HK integral. But the problem with the HK integral is that it was ported from Hölzl and nobody besides John Harrison really understands really this conversation. Yeah, so type class hierarchy. So of course we as I said, we started with the real numbers, with complex numbers, with Euclidean spaces represented as vectors of reals. So we introduced the Euclidean space type class, but then of course we want to have, for example, a real known vector, a type class of real known vectors when we want to talk about more complex types like bounded continuous functions from a topological space alpha into a real known vector space, which was important to prove Picard-Lillard, for example. But you also want to have metric spaces where you have, for example, a type of finite maps which have an explicit domain, which carry an explicit domain. And the problem is that even if beta is a real known vector space, the maps are itself with an explicit domain are not a real known vector space because you don't have a unique zero, for example. And you want to have topological spaces, for example, for the extended real numbers. While you can add an arbitrary metric to it, it is not the canonical metric you want to work with. So I mean, you want to have topological spaces anyway because they are the foundation of limits.
What does the F stand for?
Sorry?
The F?
The F is for finite. It's a finite map.
Your hierarchy is all very nicely nested, but what if I wanted to sort of do
If
my
you
type
can-
classes in, you know,
Yeah,
in
it's just,
bits,
it's of course
there's
just like,
something quite good about not doing it one
Yeah.
thing on top of another. But
of course, I mean, you have, for example, a complete spaces which is a complete separate hierarchy to, I mean, you have a complete metric space, you have a complete.
So does Isabelle's type class hierarchy?
Yeah, it is very nice because you actually can talk about intersections of type classes. Yeah. But it's not always used. Sometimes you have actually like a linear ordered semi-ring with one or something. Then you have a very long. If you need coherence theorems between the abstract concepts. I mean, this is just to of course we have more than 4 type classes, but just yes. Few more. 2 or 3. start with topology itself. And of course, before we do topology, we want to first have a abstraction for talking about limits. And for this, we use a concept called filters. So to explain what a filter is or why we want to have it, I just step back and then see what kind of limits we want to talk about. For example, we have the limit of a sequence x when it goes into natural numbers to infinity, goes towards a real number L, for example, a limit L. And then we say for all epsilon, for all positive epsilons, there exists an n such that small n, after n, the difference to the limit is less than epsilon. But we can also generalize, or we can also talk about functions going towards a value a, or the limit of a function when I go towards a, where I then have here, if you look at the green part, I have a different expression here. So I talk now about a delta environment around a, not including a, and I want to say that for each epsilon there exists a delta like this. But then I have the problem that sometimes I want to approach this limit from the left, or from the right, or from the left, or that I want to reason about how a function behaves on the real line at infinity, or maybe minus infinity. And of course, you don't want to have 5 or even more different concepts to express this kind of limits. You want to abstract over this. And for this, we use filters, because filters allow us, filters are predicates on predicates, or sets on set of sets. You want to see it, which are closed under intersection and are closed under upwards. So bigger sets are always in the filter. And then you can just say, okay, now I abstract the sequential part and say, okay, now for a predicate, I want to have the property set after a certain point, the predicate is true everywhere, or for point A and the predicate, I want to have the statement that the predicate holds in a neighborhood of this point. And then we can express that now some function on an arbitrary space goes towards, or on a topological space, or a metric space in this case, goes towards a limit L on a filter F by saying, okay, for each epsilon environment, the environment, the filter is true on this environment. And for this, so with this we can abstract all these cases here, but we can even go one step further and say the limit we want to talk about in this case is a concrete element of our space, but we can also say, we can abstract this and say again that's a filter. So when when we approach, for example, x 1 divided by x, and we go to 0 from left, we want to express that it goes to infinity, which again could be expressed as a filter. So we want to have expression saying a function f on a filter f goes towards filter g, and this also allows us to, for example, has a nice compositional behavior. So we say when a function f on a filter h, f goes to h, and g on h goes to g, then we can compose them and say, okay, this composition goes now on this filter towards that filter. And a nice example is where this one, where we say we have the exponential function of 1 divided by x, and how does it behave when we go towards x from the negative side. And the interesting thing is that we can reduce the amount of proofs, of course, by just splitting it into a compositional system. So that's one of the central parts of the foundation in Hölzl analysis, to try to express a lot of things as filters, because they allow very generic and very nice generalization. Then, of course, topologies itself, we formalize them as using the open sets, and then we can construct the neighborhood filter, and we can express limits. Then, of course, we can introduce.
So you're using open sets, not the basis.
At least how the type class is defined, to say, okay, we have open sets, which are like which are closed under union and intersection, but you can also use generate the topology from a basis. Yeah. We have this concept of generating a topology from the basis, even a subbasis. And then when you when you want to talk about the neighborhood filter of generated, you get the fact that for subbases, of course, you need to have a finite intersection of your elements and subbases. Yeah, we can talk about, of course, continuous. We have compactness and connected, and here already is a small difference. Usually in topology, topology books talk about compact space or connected space, and assuming that all your topology is actually this kind of, that you have one topology on the entire space and it's compact on this entire space. Yeah.
I have a question here. Your notion of converging against a point or a filter, it always involved this epsilon thing. I remember from the last.
Yeah, sorry. I mean, this is now it's more abstract. So the neighborhood filter is really talking about open sets. So sorry. This is a special version for how it looks for metric spaces.
Okay.
And for open sets, we say, okay, for all open sets containing X in this, no, sorry. For all open sets containing L, I mean, now we are on the range, F of this open set should hold. Yeah, and this is it. So in our case, it's compactness and connectedness. Is this, Martin? Is this?
That is
Okay. So this is already relativized to a set. So you don't say my type alpha is open, is connected or compact, but we say you have a set on alpha, and in our this set is now in our relative topology is connected or compact. But then we have, of course, a set of type classes for special topological spaces like separating spaces, perfect spaces, countable topologies, order topologies, and so on. And the nice thing is now, for example, if we want to talk about the extended real numbers and then also the real numbers, of course, so there are a lot of analytical definitions and concepts one wants to use already abstract here for both versions by just assuming that they're actually in the right kind of topology. And then, of course, we also have uniform spaces, but it's not very well developed, but we have metric space, and here, for example, we have the concept of complete spaces also.
Locally compact?
No, compact is usually expressed as
Locally compact.
no, we don't have locally compact. It was
What
not
do you mean
this.
we sure we do?
Locally compact?
Well, depending on what it means.
I mean, we do not have a type class only
Not as
expressed.
a type class.
We have locally compact
There's-
spaces,
yeah.
but
Well, there is this locally thing from whole life that you can apply to things, and there's a whole bunch of good theorems.
that's true. Yeah, we have. I mean, we have the concept of locally compact, but not as a type class.
As usual, I have no idea what it refers to.
Every point has a compact neighborhood.
Yeah.
I see.
The point is that
Very fine.
the nice topological category is locally compact.
Well, I
because
forced
it's-
it, but as usual, it didn't mean I.
But interestingly, we don't need it. That's the. I mean, or maybe later in complex analysis, it's maybe more.
I don't remember where it's used. It's a huge, vast bit of wonderful machinery.
Yeah, then as I said, we have metric spaces, and now real vector spaces, and of course now this is based on the algebraic hierarchy in Isabelle, so it goes from the abelian group on the additive operators, and real vector space extends it by scalar multiplication. And here we have another problem in Isabelle, is that type classes can only talk about one parameter. So we can talk about the vectors itself, but we cannot talk about a k-vector space and abstract the field here at this point. The field needs to be fixed to the reals.
Is that a fundamental problem, or just because nobody got around to doing something
I
with
think
it?
it's fundamental in the sense that type classes should be always should be decidable. And I think if you allow two parameter type classes, you reduce this factor. So, I mean, of course, in the logic itself, you can work around it, but not the type class mechanism as we have in Isabelle. Yeah, then it's extended to a Riemann space, so we have a metric, and we get, of course, the limit. We get that the vector operations are continuous, so we get also limit facts. We have the Frege derivative, which gives us also the derivative on real numbers, for example. And we can talk, for example, about bounded continuous functions, as I said, which is interesting for Picardie. Yeah.
Sorry, it's a question of the previous slide. So you said R bar is in all these type classes. So R bar is
Not in all, but then, for example, what's important here is that they're
okay.
in the order topologies, and I think actually in this case, yes, they're in the separating spaces, they're perfect space, they're countable.
So it's R plus 1 point.
No, it's plus minus infinity and plus
Okay.
infinity. It's extended real numbers. I mean, we have now also the non-negative extended real numbers, which are very important for measure theory.
Now you could add 1 point to make it compact. Compactify.
Yeah, okay, to get like the circle. It wasn't
Okay,
necessary yet, so yeah. But it's a nice topology, yeah. Yeah. So and of course we have real inner spaces, which gives us a norm. So actually we directly derive it from real vector spaces, but then proves that each real inner space is a real vector space. And of course this gives us arithmetic infinity.
Is there a way in Isabelle to override a type class?
No. Alright,
Because you do happen to work with multiple topologies on the same on the same sets.
Huge limit, yeah. So when you have, I mean the canonical example in Isabelle is usually lists where you want to have a prefix order or you want to have a lexicographical order, and there's always a little bit fight which one should be the default instance, and we don't have any instances because you cannot change it afterwards. And that's the same here as having different topologies on your spaces.
How can Lincoln toy around with using an alias to
of course
to have a different.
I mean, yeah, it's. I mean, you can of course make a copy of your type and assign different type class instances, but this is not for free, so it's quite some work. Especially you cannot do it in a group. Yeah. So now, sorry, we're. This is like the foundation where most. I think most things building on top of whole analysis or in whole analysis build on this hierarchy of type classes. Then what I want to show a little bit is how actually now back to a little bit history and then see how this generalization evolved over time. So a very important fact in analysis, of course, that when you have a continuous function and you look at the image of this continuous function on a compact set, that you actually have a supremum on this image. And so the original proof, or one of the first theorems, was by Florian Paulsen on now very concrete on functions from reals into reals, on concretely on closed intervals, and here even the problem is that what you express here is continuous, tells us that it's continuous on the interval AB, but actually on an open set around AB, so a neighborhood of this interval, and then we know that there exists a maximum value in this range. Then what we parted from Hölzl, what Robert Himmelmann parted is a nice generalization first. We talk about Euclidean spaces here, going to reals, and we talk especially about compact sets instead now. We don't not about cubes or something, but now arbitrary compact sets, which is a nice generalization. But we see here that the continuous in Hölzl talks from real to n to a function on real to m. So we need to embed actually the real into the Rn1, which is not the same as but luckily with type classes we do not have this problem anymore. We can even say, okay, now there's an arbitrary topological space, beta is a linear order topology, so where we know that the closed intervals are open. And then we can derive that for each compact set and continuous function we know that exists it attains a maximum.
I just invented that name. Or like the called lift and drop, yes.
Yeah, maybe yeah, it has another name, yeah.
Because only R1 counts as a vector space, R doesn't.
Yeah.
That's the problem with the way they do it in Hölzl.
Yeah. I mean, units, like I think even in Coq you would, when you would use like finite vectors, vectors of length 1 is not equal to the type, the element type.
Well, depends. If you do it, you can do
It
it with
depends
like
how-
class and
yeah.
and then it
If you
works
construct
fine.
it an induction, or an recursive. But at least in whole, of course, it's a very different if I have the function from unit to reals, or if I have just a reals. Then I first a comparison to halide. So as I say, we can generalize this nicely now to type classes. A difference is also in a halide. I think most limits are expressed as nets. So it's I think it's even isomorph to filters, but the representation is quite different. And I think you need an additional type in your concept, which is more difficult. And we try to unify the available theories in Isabelle more and more. So it's still going on and it takes a lot of time, but especially, for example, we unified the original analysis formalization by Larry and then Jacques Real, and also try now to integrate more and more of the measure theory back into the analysis. Then a couple of applications. So Fabian started, when did you start? 5 years ago, working on ordinary differential equations and dynamic systems also. And now the idea is to get more and more on the proof of the Lorentz attractor as a nice application. So the Lorentz equation were developed by Edward and Lorentz. At least that's what Fabian told me. He was a meteorologist, and then when analyzing the weather, he came up with these equations, which turned out by numeric simulations to be, it appeared to be chaotic, and it was so important that Steve Smale put him in these problems of the 21st century, and then at some point Warwick Tucker proved it using a computer-assisted proof. So there's a huge numeric computation assigned with the proof itself. And the hope is that first we can prove the correctness of this computation by doing it in a certified way, which I think is nearly finished, or is already finished.
I talk about it.
Yeah.
On Thursday.
Yeah.
So what is proved? I mean, what is the statement of the result?
More or less that the computer-assisted part is verified.
No, not of your result, but of this Warwick's result, or Tucker's result.
That the Lorentz equations give rise to a singular hyperbolic attractor. The precise notion of chaos.
So that's the Lorentz attractor, that's chaotic. And for this, of course, we need to have a lot of mathematical background, not only for the numeric computation, but also when we want to get more and more of the further analytical proof. For this, we need to talk, of course, about differential equations and dynamical systems. And one important part here is to talk about the flow of an ODE. So let's say these are the solutions, or this is, for example, a flow in the three-dimensional ODE. And this flow here describes, for example, the motion of a particle in our ODE field. And we have now in Isabelle the proof that this flow is continuous and differentiable depending on the initial condition. And for example, one needs also to talk about the Poincare map, telling us when we start at this point and the flow goes around, where does it end up in this Poincare cut. And then this is now, for example, this is now a nice entry in the AFP also. Another thing we have in Isabelle is now measure and probability theory, which is heavily based on the analysis, and which is formalized in a very different way actually. So the problem is that when you talk about measures, you often are interested in a subset of the actual type you're talking about. So now measure especially needs to have an associated measurable space, which could be like topology assigned as a type class, but then we have also this limitation of type classes, and also we want to have an explicit carrier set in our measurable spaces. So here meshes are explicit type compared to topology where meshes are a type class. And then we have the usual stuff. So we can construct measures. We have the Lebesgue measure on real to n on Euclidean spaces. We have product measures, and they're used for a couple of applications in probability and stochastics, like saying we have now infinitely many independent random variables. We can analyze Markov processes, and for example, we have central limit theorem, thanks to Jeremy. But yeah,
Is there a good example? So what's the most natural example of where you want to have a measure on some subset of a type rather than the whole type?
I mean, one problem is if you want to talk about product spaces. So you want to talk about, we have n independent random variables.
Okay.
And usually this n is not fixed as a type in your proof, but it should be a natural number. So you say, okay, now I have a sequence of.
Okay, so that's because simple type theory can't have
Yeah.
type dependencies.
You cannot have term dependencies. I mean, there's. This one shouldn't forget that there's often in 90% of all cases there's a way to work around this, but then it gets really ugly.
There's always a way.
So yeah, now to integrals. So most people know the Riemann integration. Maybe they learn about the Lebesgue integral, which is an extension of the Riemann integration, Riemann integral. But since there's, and then one important part is also, so it's already on the Euclidean spaces, it's an extension because you have dominated convergence. But the Lebesgue integral also is an integral on arbitrary measures especially. But now we also have a very different, a slightly orthogonal integral, the Henschel-Kurzweil integral, for example, which allows us to integrate over functions where the upper half and the lower half is not finite, but which cancels out, for example. And in Isabelle, we have now the problems that we have these two kind of integrals which do not perfectly match, actually. So I invested a lot of time to develop the Lebesgue integral, and then Larry invested a lot of time to port it from Holite and also to try to understand it. But it's not 100% clear what are the relations between both integrals. We know that the Lebesgue integral is actually the absolute variant of the HK integral, but the question is if the HK integral can be represented completely in terms of the Lebesgue integral, which is not clear to me.
I had the interesting experience of asking a number of mathematicians what they knew about the gauge integral, and none of them had heard of it. But the other interesting reaction I seem to get is this is a bit like asking a Formula One racing driver about the exact kind of material used in the brakes or something. They really didn't see it as relevant to what they did, as long as the car stops when they wanted to.
Yeah.
But if you have a Lebesgue integral function, and you take the absolute value, it's still Lebesgue integral, and that doesn't help really.
Yeah.
There are things
They're not
like
the same.
gauge.
Yeah, so they're not 100%. So they're slightly orthogonal.
Yeah, they have non
Yeah.
overlapping,
Yeah.
but not.
When were Henstock and Kurzweil inventing their integral, roughly speaking?
When?
When?
In the 50s? Actually, I don't know, but I guess.
One thing I learned is it's a kind of a slight generalization in the Riemann integral. Is as I recall, the Riemann is you take the region and you divide it into rectangles. When with that one, you still divide it into rectangles, but they don't have to be the same width. I believe that is one difference.
That's correct.
And that somehow makes theories much more general. But it's actually quite an easy thing to understand. I mean,
Sounds almost trivial.
Yeah.
It's just a bunch of rectangles, but because they're different widths, it's much messier to work with.
It's very annoying.
There are rather a lot of the rectangles.
Yeah.
Well,
But yeah, I mean, and then this is all, of course, embedded in the set of measurable functions. So we have three different, because I mean we also have what I call non-negative Lebesgue which works now on the extended non-negative real numbers, which can return infinity. So the nice thing with this one is that it's defined on all measurable functions. And can be used to, for example, say when is a function Bochner integral, because when its norm is has a finite integral and is a non-negative Lebesgue integral, then it's a Bochner integral, which is a very nice way of working with it. As I say, the Bochner integral is a generalization of the Lebesgue integral to vector spaces. If people are not familiar with it. And as I say, we have, so in measure theory we have, of course, the Bochner integral because it's the final measures. Hölzl uses the HK integral, and that's why we have it also in Isabelle. And we know that, as I say, the Bochner integral is the absolute version of the HK integral. So if the non-negative Lebesgue integral on the norm of f says it's finite, then these two values are actually the same. But of course, the problem is that it would be nice to have a abstract concept of integration where we could just instantiate.
Just move on to Stieltjes.
I don't know if this is, it doesn't generalize both, does it?
Generalizes Lebesgue. Just allows for point mass.
I don't know. Does it? But I can always derive a measure from Stieltjes and then have and integrate over the measure itself. And then one problem is HK integration is, so for Lebesgue integral we have this nice concept of talking about measurable functions which do not need to be integrable, but we can always say when we find a measurable function and we know a bigger function which is integrable, we know also that the measurable function is integrable, which is a very nice fact and very helpful actually. But this is not available for the HK integration, unfortunately. Okay, so then more to a couple of decisions we made, problems we had, and solutions we found. Well, first, of course, we embrace undefined values, but in mathematics procedure cannot understand, so when you divide by zero, we return zero, we don't.
I'm claiming credit for that.
You also got 0 equals 1 in there.
But I mean, this goes further. For example, for the log functions, we want to at least that it's constant for if it's non-negative on its non-positive part, because otherwise it's hard to prove that it's measurable at all on R as example. And I mean, for measurability, you want to be close on everything, so you want to have this kind of effects. But also you want to have, for example, that the integrals are 0 if f is not integrable, and then you get at least effect like this. It's not much, but it's a little bit, which if you have something like a simplifier, it's very nice to work with. Then it's not really related to undefined values, but for example, filters. In math textbooks, it's often, filters are always introduced, or often introduced as proper filters. So you do not have the set of all sets in your filter. But then you have the problems that the proper filters are not a complete lattice. But if you add the non-proper filter, you get the nice effect that this form a complete lattice in non-proper, so including the non-proper. Also, it allows us to actually, when we at some point we need to prove that a filter is proper, and then we can still use all the constructions from our filter library without assuming that it's proper in advance, for example. And I think this holds, of course, for more than just filters. I mean, it would be always interesting when we had a type of measurable function. Sometimes it's nice to first construct your type and then prove that your type is actually in your set. And also stuff like having extended versions of your numbers, for example, talking about extended non-negative reals, simplified a lot. Also, compared to the extended reals where you have negative values, which usually do not need.
Okay, can you explain again this log is constant?
So one idea of introducing log would be just saying, oh, it is the function which is inverse on the positive side, is inverse to exponential function. But then you do not know anything about how it behaves on the. You cannot prove anything about how it behaves on the non-positive part. So, I mean, the obvious solution is to just say, okay, for each x, you know that either x is non-negative, and then you just return 0 or whatever, and if it's positive, you return the exponential function. I mean, that's just a small part, but if you try to do it for each function, you can always derive that all your functions are measurable, for example, even if they have undefined values which you do not really care about. Does that make sense?
It's just convenient.
Yeah,
It's
just convenient.
measurable outright.
So you have theorems stating that log is measurable in R.
Yeah. Even if most mathematicians would say, oh, but it's undefined there, but in the total logic, it's much nicer if you have this result.
So it's the same kind of trick as the first time.
Yeah. It's an extension of the first one.
Thank you.
Yeah, and then of course a huge problem is this difference between type classes, type predicates, and predicates of sets. So as I say, type classes are very nice. We want to use type classes because they integrate with the kernel even. They work, as a parser works well, so when I write down a constant, the parser can infer which kind of type we want to use, or which kind of type class we want to use, and it's of course also integrated in the automation like the simplifier auto and so on. But then we have the problem, there's only one pi parameter possible, so we cannot talk about k vector spaces. And we can only associate one instance to each type, which is also an analysis, sometimes a restriction. So one solution is of course to use type predicates to talk about the operators of your type class here, and say that they fulfill the type class equations. And then you have more than one instance per type, more than one type parameter. But sometimes you even need to go first and say, okay, actually we are restricted to a set also, where our operation, so a carrier set. And then you need to say, okay, now all our operations, the equations or the assumptions in our type class hold when we are in this set. So another thing is, of course, this allows most constructions, product constructions, even some quotient constructions and so on, can be, when you need to do a lot of these kinds of constructions, you want to have this style. But then the other problem is that this is not very well integrated in your automation. You need to carry around a lot of assumptions that you actually essentially the result of your operations is again in your subset and so on.
You don't for type predicates.
No, you don't need this for type predicates, but still you need to carry on the type predicate to all your to all the lemmas you want to get, or you need to
But integration, how are type predicates better integrated than set predicates?
Because I do not need to talk about this. I mean, sorry, but actually what I wanted to write is that A operated B is again in S. And you need to, and then with set predicates, you always need to prove actually that the result of your computation is again in the set. Where in type predicates, you get at least this from your type inference mechanism. But then we have, as I said, we have measures. And actually we have also the concept of topological spaces, again, completely separate to our type class hierarchy, again, as structures, because sometimes you want to have this construction mechanism. It's not used often, but it's still there. But what one should not forget is that often one can work around these restrictions to sets. Or to have a set, instead of having a set predicate and saying our topology is defined on the subset, sometimes it's enough to say, when we want to talk about like log, that we have actually like a restriction on our morphisms or on our concepts like open sets or closed sets. But I think that's also done in SS Reflect group homomorphisms, as far as I understand. So you say you have a morphism F between two groups, but actually it's from a subgroup, and we have a restriction on a set.
Yes.
Yeah.
But because it's Carc, you don't have the type class restriction, so we can infer that it's a morphism using the type class mechanism because it's not restricted to the types.
Yeah, I mean, but the inference is still easy in Isabelle because it's just called auto, and auto does it for you, usually, if you're lucky, if the rules are set up in the right way. Yeah, but For structures, in Holite everything is expressed as R2n. So you have these functions from finite space into reals, which is of course describes all Euclidean spaces or can represent all Euclidean spaces. But it's still interesting to have an abstract concept saying alpha is a Euclidean space, because then you have these nice features that you can say serial numbers are a Euclidean space.
Integrable functions are also a Euclidean space, right?
You
get a dot product by a convolution.
Yeah, but they're not finite. So they don't have a finite base.
No, it's still
But yes, they're really not like a space. Yeah, and of course it would be nice to say, okay, by the way, this is also we have this concept, for example, with bounded continuous functions, but the problem is also possibility using a subtype is a big hassle.
One of the ugly things in Holite is that the complex numbers have to be identified with R2. Now you might say, well, sure, they are like R2, but still the idea they have to be is kind of ugly. And then you can say, oh, our complex numbers are our co-data type.
Yeah.
And also that there's a significant distinction between R and R1, and that a lot of these proofs are full of these bijections between R and R1, because only R1 is a vector space and R is just the real. So again, it's really quite ugly.
So this is, that's something I think I learned at least doing this part to realize that even if we have a canonical representation, it's still nice to have an abstract description also, and state your theorems in processes abstract terms. And also, often you want to just introduce a type to harvest certain theorems from your theories. That you, for example, we actually don't talk often about bounded continuous functions, but to have bounded continuous functions allows us to, for example, for Picard-Lindelöf to get the Banach fixed point theorem, and suddenly we have it on functions. And it's not that we do a lot of operations on bounded continuous functions, but it's like the harvesting.
Yeah, but if you develop more of the theory,
if you maybe when we get more theory. What's unfortunately not often possible in Isabelle and AGL to actually have type constructs, but which would be very nice because, currently we can easily construct product spaces, but most other constructions on types are forbidden because we cannot express them nicely in terms of our type classes or of types itself and embeds in our type classes. Okay. With this, actually, I end with Isabelle, and I want to go. I don't know. I have 5 minutes, or. So Lean is the new contender, and I want to work with Lean, and I work with Lean. So we also, of course, want to have an analysis, and the idea is to base the analysis of the concepts we learned in Isabelle. But I need to admit that currently we do not even have serial numbers. We are currently working on topology and uniform spaces to get to the point that we get serial numbers nearly for free. So how should this work? As I said, it's based on the ideas we learned from Isabelle. And one thing I also want, for example, is to have to prove that, for example, topologies build a complete lattice, and then you get a lot of theorems for free when you want to construct products or when you want to construct quotient spaces and so on. And I think always a hard time is finding the right abstraction to get not too abstract, but then to still be possible to develop what you want to develop. And this will change with time. Sometimes somebody wants to prove something new and needs a new abstraction. So first, what we already have are topological spaces, so we can actually prove that they are a complete lattice. This is about filters where we have nice algebraic properties, but we also have, for example, alter filters. And then for topological spaces, we also have the concepts that they're a complete lattice, and we have like map and co-map. The induced or the co-induced topology, and which allows us to have a very nice construction of products, subtypes, sigma types. And currently, prop is introduced as a Sierpinski space. We have, of course, continuous functions, which are nearly for free when we construct this product construction using map and co-map. And then to now introduce serial numbers, we want to have the idea is now to define your functions on rational numbers, which we have already, and just have an embedding and then somehow lift each function from this embedding into the real numbers, which we construct as a completion. And the hope is that it works in the following way. The first, of course, for the range is not a problem. We just compose it with our embedding. So the question is now, how do we lift a function which goes from the rational numbers into a complete space? So C is not the complex numbers, but the complete space. And then we want to construct a function f hat. And this hopefully works, or well, in mathematics we know that it works by doing the following construction. So we start with x. We build a neighborhood filter around x. We apply the co-map, so the inverse map on filters onto Q, which is now, of course, which may not contain x, so it's not really a neighborhood filter, but it is at least a Cauchy filter. We know we can prove that it's a Cauchy filter, and then we map this one along f from Q to our complete space, where we again get a Cauchy filter, but now we know that we're in a complete space, so we can extract the limit from this. And this is a very nice, this construction then allows us also to have very nice proofs. But to do these constructions, we need to talk about uniform spaces, we need to talk about completeness, so we also have uniform spaces now. And I should also say that these constructions of the real, of course, is not new. It was done by, it's a standard construction as done by Bubaki. Christian Lillet uses this, I learned in Unimath, and Robert Krebs and Bess use it. Very similar, or actually, I guess the same approach.
Yeah, but it's not too old.
Sorry?
It's much older.
It's much?
It's much older.
Older. Yeah, of course. I mean, the basic idea is already defined, and you just by Bubaki. But of course, the hope is that we can, of course, introduce everything on, or most stuff on uniform spaces, and then to define the real numbers is just a couple of lines showing that they form that the rational numbers form a uniform space, and then all the operations are either locally uniform or uniform on the entire space. Yeah, and then, yeah, so we just want to use them as the Cauchy filters on Q, which is the completion. And then we can, to hope, or the idea is that you have a proof like you want to prove that a plus b equals b plus a, so that the addition is commutative, and we can do this by saying, okay, now when I have the product space of R is the closure of the rational numbers, which we know because rational numbers are dense in the real numbers. Then we know we can say that this is actually a subset of all B for which this property holds, because of course commutativity holds on rational numbers, and then we can remove this closure because we know that this is a closed set. And this, most properties, or all these properties are very general properties which we have anyway. So talking about density, talking about closeness of equality should be a property we get from topology. So this is not something very specific to the real numbers. This is something where I hope which drops out for free. This is the end result at least. Yeah, sorry, it's something different. Okay, so that's all. Thanks for listening.
How long does it take to compile the Isabelle analysis library?
How long it takes?
Yeah.
I don't know.
45 minutes on my computer.
Yeah, but you have a very fast computer.
It can be done in about 4 minutes if you have a decent computer.
Sorry?
About 4?
Yeah, I mean, if you have a modern computer 4, I have on mine it can take up to 10 minutes. It depends. I mean, it's a nice thing. It's Isabelle runs on Polymer, and it's nicely parallelized. So.
Now, a whole light takes hours. I couldn't say how long. So if you want to actually run a whole light proof, you have to load in all the sources every time. Whole light loads in, I don't know, a minute or something. But then the analysis library at whole light, I may never try to measure it, but it's certainly at least 2 hours, I would think.
Okay.
And of course, once you close your session, you have to load it again.
But I mean, you can. There's this concept of, or there's these tools which allow you to have a copy of the heap.
Never figured it out.
Okay.
On a Mac Pro, anyway, the Isabelle analysis library built in about
are you planning to use these undefined values in Lean?
Yeah, I mean, as I didn't say it maybe, but it's on the first slide I mentioned that the idea is to develop a classical analysis. So we are fine with just using.
Yeah, but still, I mean, if you have dependent types, you can be more expressive.
Yeah, but this always restricts your. I mean, as I said, sometimes it's much easier to compose your function space and then prove afterwards that it's measurable, that it's continuous, or is it's integrable or whatever. Instead of thinking, I need to figure now out why this is positive at this point, for example. Or when you integrate over 1 divided by x, you often don't need to prove it because you know that the zero set is actually in this case.
Well, the system could just generate a side condition and maybe automatically resolve it. So,
Yeah.
Jeremy, what's your opinion on this?
Well, I'm just pragmatic. I mean, whatever, you know, I'm more
Whatever
interested
works.
in one that works and is usable.
The question is, what is most workable?
Yeah. But so what's the advantage of not doing these tricks?
That you might shoot yourself in the foot at some point?
And how, what is the concern? I mean, so you do have to, so I mean, to make sense of your theorem, you have to tell your mathematicians, this is how we're interpreting divides. I mean, you are cheating, you can be honest about how you cheat. But what is the concern?
That at some point you prove something that you didn't expect, and then use it later on, and then you prove more things that you didn't expect. And then you spend a lot of time figuring out what actually happened.
As long
But
as you can understand.
That's fine, as long as they're true.
I don't see the problem.
Yeah, I mean, this can also happen when you do not use undefined, or when you do not use. I mean, of course, if you're mathematicians, you may wonder why it goes, but then in math books, you often write down exactly the same equations, and you know what your side conditions are.
Is there any any evidence of analysts actually wanting to use these things themselves?
Yeah, for example, there's now a very nice ergodic theory library in the AFP, developed by a mathematician in France, Sébastien Roussel, which I heard he's known in the ergodic theory community. I hope that's correct. As you know, at least.
Do we understand what their motivation might be?
Actually, I don't know. I mean, so he had a new
Is it,
theorem.
an alternative to playing video games?
So he had a theory, or he developed a new theorem or a theory, I don't know, and he wanted to formalize this in a computer system. So he chose Isabelle because we have the measure theory, which was necessary for this.
Did you try to replicate the simplifier automation you discussed yesterday in Lean?
Yeah, I mean,
Since you now have dependent type classes, you can actually use type classes to show functions are
Yeah.
continuous
this is
and the like.
it's not here if you want to use the type class mechanism, because the type class mechanism has a hard time working with function composition, or with function writing lambda, essentially function composition, because I think the idea is that
Well, you can always write f as f composed with the identity. So
Yeah.
you have to be careful.
yeah.
I think for speed, I mean, higher order unification is kind of limited in type classes.
So I think
Well, I mean, the same, you had the exact same problem yesterday, so the same solution should work. You just need to formulate your type class in this way.
yeah, this would also work. But the other question is if you need it in the type class mechanism, or if it's enough to integrate it into the automation, like the simplifier or the SMT tactic to do.
Yeah, I mean, there's still something that we need to figure out. But
Lean likes to, or at least Jeremy likes to build proofs explicitly in Lean. And if you have it in the type class mechanism, then it will kick in
That's true.
there.
yeah, but there are other mechanisms to get things to kick in automatically. And the question is whether you need to solve it at parse time, or whether it can be a goal that's left until after the elaboration and then solved after.
So
it's a matter of when and what kind of automation.
So there's now, for
how
example,
much you want to configure the automation.
I mean, we have, for example, autoparams now. So you have an implicit argument where you can say, okay, if you need to solve this, here's a tactic. When you write down your theorem or your definition, And then when the user writes down your constant and Lean sees that there's an implicit argument used or solved by this tactic, it just calls a tactic. So you can say, okay, you have measurable statement, calls a measurability proofer or the continuity proofer. If the type class mechanism is not powerful enough to handle it. So that's it. Yeah.
A general question. 20 years time, how do you think Lean versus Isabelle versus
And then 20 years.
10, 20 years?
Lean
What's
will
the
be ruling the world.
long-term plan? So I can see that kind of you're moving stuff from Hollight to Isabelle. So replacing Hollight with Isabelle will Lean replace Isabelle.
I guess it will. We will see. I mean,
Everybody will be using cock instead.
I mean, the difference, I guess, is that in Coq, I made the experience that a lot of people want you to do constructive proofs. So I was not interested in trying anything in Coq, but then Lean appeared, and everybody was like,
I was just thinking in 20 years there will be like how many generations of American graduate students who maybe know cock.
I mean, but different theorem proofers have different strengths. I mean, there is the important question of how to coordinate and share libraries and things like that. But
I mean, I think we shouldn't forget that theorem proofers are still an academic product. So if Larry is not anymore working in 10 years on Isabelle, if Tobias stops working on it, it depends if there's if Gavin continues to work on Isabelle, if there's always new influence and extending. And we shouldn't forget that the software is now really old, so it has a lot of, we need to refactor a lot to keep it alive. And then, I mean, that's also the case in Coq, I guess. Yeah.
One
And that's a
problem
nice
Lean
thing
doesn't
with Lean.
have. Well, actually,
It's
it
now
does, right? It's been
a new
refactored
start,
twice.
and the hope is that more standardized to have a safer future.
What we do know is that all these systems will be talking back to you, right? You know, hey Isabelle, prove my theorem. I know, I'm going to prove this other theorem.
I think speech recognition could, even in the near term, could be used for finding stuff, especially with your filters. And the whole problem with filters is that the usual mathematical terminology doesn't make sense anymore. So if you were looking for a theorem about the limit of a sequence, you can't find it because it's something to do with the filter. And that's where one could mediate with something that would initially with some keyword-based thing, but maybe ultimately a natural language thing that says, give me what we've got about sequences. And if it's done intelligently, it would have some of the more general things, which are not only for sequences as well as ones that are specific to sequences, even though they're all about filters.
Yeah. So, but this again, this sounds also very strong like proof search. Again.
Yeah, I'm talking about search.
Yeah. You also, Vincent?
Yeah, I had two questions. One was about automation. So what do you think would be good, the right, the necessary tools for automation related to analysis? And the second one, well, you've already discussed this number. Second was what about complex numbers and complex analysis?
Oh yeah. So first, complex analysis. I didn't mention it at all, but I think Larry is porting a lot of complex analysis from Hollight. And I need to admit I don't understand most of it. I'm just not into complex analysis.
I really don't either. I never studied it. Just give one line at a time. And I gave a talk. Were you were in Paris? Yeah, I saw my talk.
So I was interested also in hearing your plans in lean analysis. So it's written lean analysis, not lean real analysis. So maybe
yeah.
thinking that
My hope is to actually have a broader foundation at least to say we have to have a good linear algebra in Lean, for example, which is in Isabelle we have a lot of different linear algebras and they are hard to unify, especially due to the problems that some practice specific or formalized with a carrier set, others are on a type classes, others are on a specific type. And though in Lean we would have the option to have a very unified approach to linear algebra. Then also I would like to have more interaction of algebraic topology, for example, to get, I mean, proving Brow's fixed point theorem without algebraic topology is a huge, very elementary proof in Isabelle currently, and I think also invariance of domains was it's a huge proof to get into, and
I have no idea which bit is actually invariance of domain, but there's this colossal amount of stuff before it in the file. Whether that's all part of the proof, I have no idea.
But of course, I mean, the hope is that when you have a very broad foundation set, developing more complex analysis is much easier because you can use these tools and have an easier approach to it. Also, I mean, it's surely very nice to just say in a proof, oh no, we need to construct this special kind of functions and proofs it's a uniform space, or it's a real non-vector space. Without the hassle to actually go outside of your proof to find a special type like bound continuous functions and then continue.
Perhaps one last question.
Yeah, I think Bas
I already had a question, but
We can do two last questions.
so what are you still missing most from Isabelle, or do you advise everyone just to move from Isabelle to?
No, I wouldn't advise, not yet at least. What I miss in Isabelle, so I think I miss.
What you miss in Lean?
What I miss in Lean. So let's say I miss in Isabelle the tools from dependent types, and in Lean I miss analysis, I would say. But yeah, in Lean, I mean, I still miss automation like we have in Isabelle. We have now in Lean a simplifier. Larry implemented on basis of, we have a concurrence closure from SNT-like concurrence closure, and Jeremy developed a couple of automation on top of this methods, and but I still miss like the auto function we have in Isabelle, which is a nice, where you simplify, then you apply intro and elimination rules, and you simplify again, and mostly just because I'm used to it, I know exactly how to use these tools. I hope that finishes also at some point. That's exactly this point where you just apply and you know what the behavior should be. I think is what I miss mostly. And a couple of constructions, or let's say more like a powerful transfer method, for example.
My remark, I'm kind of sorry that we've not found any use for non-standard methods anywhere. One of the nice things about the non-standard reals is that you get infinite values, but it's still a field. And also, as I recall, if you prove a thing using non-standard methods, you don't have epsilon delta arguments, and yet the results you get in the end can be mapped back to the standard reals. So you get the original theorem about the reals proved as a theorem. It went via the non-standard reals, but you can't see that anymore, so this is a huge saving of work. Whereas the proofs I've been porting all the time where you need to get a thing less than epsilon, and we're literally like that, so less than epsilon over 3, so it's that, add them up, effing nightmare, and finally you get it.
Yeah, but I mean, though I would, my proposal is to use filters for this, because they are exactly doing.
But they still have the epsilons.
No, I mean you can embed this in a filter itself.
Well, I'd like to see such a proof.
Yeah, it always, I mean, it still depends there. But my hope, for example, is that exactly this is what I want to do for Lean. I mean, in the end, to have just a proof like this here, and nothing. So the only thing where I need to talk about epsilon is to prove that Q is actually a uniform space. But everything else will just talk about topologies or very basic topological concepts. You don't. There doesn't any epsilon appear anymore. Actually.
Well, we should take some of these examples maybe and show how.
And then
they
yeah.
Okay. So thank you.
Okay.